All right, well, part 2 of notes number 2. We're starting on page 4. Today we're talking about the Cartesian coordinate plane. That's this thing right here. Okay, you've seen it before. It's a little cross thing. Ave Maria, right? So, why is this important? Why do we care? Here it is. So René Descartes, this guy, this French man, right? He was a Renaissance man, kind of like Da Vinci, where he did like everything, right? He's like inventing stuff over here, doing math, doing physics, painting, sculpting. That was René Descartes. He was also a philosopher, and he came up with this famous phrase, I think, therefore I am. It's a postulate. He said, before we can start discussing dinner tonight, right? And I say, hey, what do you want for dinner? And the response from your significant other is, what is dinner? What even is life? Who are we? Do we exist? Right? It's like, okay, hold on. We just need to figure out dinner here. You got to set some ground rules, some things that we assume and agree on. Those are postulates, right? We exist. I am hungry and I'm getting hangry, right? Those are things we need to establish before we get into this dinner thing, right? So what he did before he started his philosophy, right, was to say, I think, therefore I am. We are here. That's all you need. It is a postulate. We assume this to be true. How could it be anything else? And if not, you're not dealing with my philosophy, you're dealing with somebody else's. He also, interestingly, connected algebra and geometry through the creation of the Cartesian coordinate plane. My mouth's getting dry. So, connected algebra and geometry. What we mean by that is, at one point, algebra and geometry were not connected. They weren't called math, and these were just subjects within math. No. They were two different things. It's like science and history. Algebra and geometry were just separate. That's shapes. This is numbers. They don't make any sense together, okay? Descartes brings it together. And he brings it together with the coordinate plane. How does he do this? Well, let's talk about the coordinate plane first. It's the x-axis and the y-axis combined. So we have a vertical axis, the y-axis, and we have a horizontal axis, the x-axis, okay? Divides it up into 4 quadrants. Those quadrants have coordinates in them, and those coordinates are x, y pair. You guys have seen this all before. X comes first in the alphabet. That's why x is before y in the coordinates. Don't goof it, okay? So the first quadrant is called the first quadrant because it's the one we like the most. It's double positive. Yay, sunshine, right? So, double positive meaning that in the x direction it's positive because this is the right side of the x-axis, right? And it's the top part, the up part of the y-axis. So that's the positive direction in both ways, so it's positive, positive. If I were to put a dot right here, you wouldn't know what the coordinates were unless you counted the squares. But you do know whatever the coordinates are. They're both positive numbers, right? It's positive something, positive something. Quadrant 2 goes in counterclockwise direction, okay? So we start in the top right, because that's double positive, and we go counterclockwise around. It's negative in the x direction, positive in the y, because negative half of the x-axis. Still the positive part of the y-axis. You with me? Okay. This one's our double negative, right? He's the Eeyore of the family. Nothing wrong with Eeyore. Nothing wrong with sadness. That was the moral of the story. You guys have seen Inside Out, right? The moral of the story is that sadness is not a bad emotion. It's an okay emotion. It's valid. So, double negative, our Eeyore over here, our sadness, is left side of the x-axis and the bottom part of the y-axis. So, double negative. And we have the right part of the x-axis, positive, and the down part of the y-axis, negative. Cool? You need to know the names of these 4 quadrants, which one's 1, which one's 2, and where you could find certain points. Right? If I tell you -5, -4, you know it's in quadrant 3, which is how I grade sometimes. If you're plotting points, I see that you put -5, -4 in quadrant 1. I know it's wrong. I don't need to care, like count the squares. I just know it's wrong. Quadrant 1's always positive. Now, how does this connect to geometry? Well, if you put some dots down and you connect them with lines, you get a shape. René Descartes, I believe, invented the coordinate plane in 1600 something. So 1600 years have gone by where people didn't realize this. How, right? But he did it. He was first. Turn the page. So we already made it through 1 page, and I told you we might not make it through 3. This is the page we get caught on, okay? So here's what I do. I want you to ignore everything below this paper. We're just going to focus on this bit. And really just this for a second. What shape do you see? Triangle. Very good. It's called a triangle because it has 3 sides, right? It's called a triangle because it has 3 angles, you silly gooses. It's not a tri-side, it's a triangle. So, A, B, and C, we label the sides, right? And those letters stand for how long the sides are. Maybe A is 5, maybe A is 6, we don't know. But we do know it's not negative or 0, right? If A was 0, we'd have a straight line. C would have the slide over here to B, so it would not be a triangle. If A were negative, well, maybe it'd be facing the other way if we're dealing with the coordinate plane, but no, distance cannot be negative, okay? So, A squared plus B squared equals C squared. You've probably heard of it. It's pretty famous. It's called the Pythagorean Theorem. And it was invented by Pythagoras. Not really. We think he existed, but probably not. Actually, we don't think he existed, but maybe he did. There's a difference. Pythagoras was a cult in ancient Greek. They believed certain things about the world, and they believed a lot of it through math. Some of it not through math. Like, they believed that seeing into the sun was bad, and you could be, like, killed for that. So cults, even math ones, not good. So Pythagorean theorem says a squared plus b squared equals c squared. Do you have that memorized? Wonderful, good. That's the only bit of memorization I really need from you guys. We're just assuming that to be true, okay? It is basically our postulate, even though it's a theorem, and we will end up proving it, okay? So, algebraically, you could write x plus 2 minus 5 equals 12, and I would be like, okay, sure, that has to be valid because you made it up, right? There has to be some answer. This is valid because, I mean, I wrote it down. But what makes it interesting is it connects to geometry, and it proves something about the world. So what does it connect to? It connects to a right triangle. So here's my right triangle. Now, A and B can be either the yellow or the green or the blue parts. Doesn't matter. They can be either leg. I'm going to call A this part and B this part. C always has to be the longest side. How do I know this? Because these two parts have to add up to one of the parts. If I take two things and add them up, they're going to add up to something bigger, right? So C has to be the biggest side. And the biggest side is the hypotenuse, the side that is opposite the 90-degree angle, the right angle. Okay? So C has to go there. A and B, you can switch them out. Doesn't matter. It's up to you. You be creative, okay? So when we're talking about this, a squared plus b squared equals c squared, when we say square, we mean what? Like the shape? What do you mean by squaring something? Yeah. Yes, so a is the length of this side, right? So I'm going to multiply it by itself. Okay, a squared. Why do we call it squaring it? Because we are talking about squares here. Remember, we're connecting algebra and geometry. And you guys earlier were like, how did it take them so long to do that? Boring, right? But you've never thought about this. At least most of you haven't, I don't think, unless I mentioned it maybe. Squaring is literally putting it on a square. We're going to take that length and we're going to make it into a square. Well, it's 1, 2, 3, 4, 5 squares it looks like here. So I'm going to go 5 here just so it looks nice. That square is now a by a. So the area of the square is a squared. You squared that number. You put it on a square. I'm going to do the same thing for b. So it's b by b. The area of that square is b squared. And if we put those two squares together, it's hard to draw squares. They will fit inside perfectly this square. A squared plus b squared is c squared. Right? It's pretty dope. You know what's even crazier? The squares aren't what's important. You could take a right triangle and use that side right there and draw a hexagon with it. And draw a hexagon here and a hexagon there. And the hexagons would add up to the bigger hexagon. As long as the sides were all the same length, right? That's the magic of the squares. Squares always have the same side lengths, right? So all the sides are the same. If you had a hexagon that was regular, all the sides were the same. They would add up to the bigger hexagon. Works for any shape. That's cool. Never heard that one before, right? So when we say a squared plus b squared equals c squared, we mean that literally. A squared plus b squared equals c squared. Cool. All right, so hopefully you have that memorized now. Now I want to talk about something that you've never seen before, or if you have, you've never seen it this way. I guarantee it. Most math teachers just say memorize it, figure it out, which is fine, but then you forget it. And then you get on the test and you wonder, which way was it? And you're screwed, because you have no idea to tell. Right? Okay, so here we go. Let's look at another triangle. A, B, and C. But now we're connecting it to algebra because I put coordinates on it. Look at that. Woo! Yeah, Descartes. Okay? So here's what we're going to do. I'm going to put a dot here. What are the coordinates for that dot? You don't know. Why don't you know? Because why? How can you not tell? You can't. Why can't you? We don't have a grid. There's no axes, right? But you do know, whatever the coordinate is, it's going to be something comma something, right? And the first thing is going to be an x. And the other one's going to be a y. So it's some x and some y. What about that one? What's its coordinates? Well, it's some x, some y, right? Here's the problem. If I just looked at these, they look the same, don't they? Are they the same? No. They're both x and y's. So we're going to call this x1 and y1. We're going to call this x2 and y2. Okay? They're both x's. Well, they're different. They aren't the same. You with me? Wonderful, wonderful. Now we're gonna lose you. So check it out. Here's my triangle. Focus on it. I'll zoom in. So I'm gonna start with this dot right here. It's x comma y, right? We don't know what it is. We have no grid, but it's some x, some y. I'm gonna call x1 and y1. Now if I go down from here vertically, I hit this guy. They have the same x value because if I go to the right, x is horizontal, right? I hit them at the same time. Do you see how their x's match? They have to be. A grid right here, they'd have the same x value. They would. So I can't just call this x1, y1, and x2, y2 because these x's are actually the same. They hit at the same time horizontally. See how I'm moving horizontally? Now if I go from here to here using these two dots, they hit at the same time vertically. So they share their y values. So let me break that down again in slow motion. x1, y1, you with me? This one has the same x value. So I have to write that. Do they have the same y value? I hit this dot before I hit this dot, right? This one vertically first, so they have different y values. Cool? Now let's compare these two dots. Different x values, right? So different x values, but the same y value. Vertically, they hit at the same time. Are you with me? So x1, y1, x1, y2, x2, y2. Do we use an x3 or a y3? No. So if you do, you goofed, right? Now, A, B, and C stand for the length of the sides, right? Okay, here we go. I don't know how long A is, but pretend that I knew that dot was at 5 and this dot was at 1. What would be the length of A? If this dot was a 5 and that was a 1, how long? What distance is between 5 and 4, right? Very good. And you did that by subtracting in your head. Okay. Well, I don't know if it's 5 and 1, but I do know it's x2 and x1. So I subtract them, and that's going to be the distance that A is. That line over A means distance, okay? So I subtract those two. You tell me what they are. If it's 5 and 1, I subtract them, I get 4. If it's 6 and 7, I get 1, which is positive 1 when I flip it around, right? So we don't know what the value of A is, how long it is, but we know that if you told me what the x's are, I could figure it out for you, right? Tell me what they are, and I'll get it for you. Now, what happened to the y's, right? Why did I just choose to subtract the x's? x2 minus x1. What happens if I subtract y2 minus y2? What happens? Yeah. You get 0 because y2 minus itself is 0. Anything minus itself is 0. Duh, right? So we didn't ignore it. It just went away. And that's the whole point of math, to make things go away. And people. So x2 minus x1 is going to be the distance of A. A is horizontal, right? So of course we're only talking about how much did we change horizontally, right? What's the distance horizontally? The x values. What's the change in y? No change vertically, right? Did we change between here and here vertically? No, there's 0 change. y2 minus y2 is 0. No change. Look at this one. Between these two dots, that's the length of B, right? Did we change vertically or horizontally between these two dots? Going from here to here. Did I move left and right at all? No, so I didn't do any horizontal change, but I did do vertical change. How far did I go? If that's a 6 and that's a 2, how far would I have gone? If this is 6 and that's 2, how far would I have gone? 4, right? And you did that by subtracting. Guys, subtraction is distance. Distance is subtraction. Always. Remember that. So I would subtract the vertical parts, y1, y2. If I subtract them, I get this. What happens when I subtract the x parts? I get 0 because there is no difference. They both have the same x value. They don't go left and right to get there. There's no horizontal change. So it goes away. It becomes 0. So the length of A is whatever the difference is between the x values, right? Horizontal. The length of B is whatever the distance is between the y values, the vertical. Okay? Are you with me 50%? I don't need 100. I just need 50. Okay. So I'm telling you the length of A is whatever the difference is between the x's. B is whatever it is between the y's. Why is A the x's? Because it's horizontal. Why is B the y's? Because it's vertical. Pythag. Instead of A squared plus B squared equals C squared, I just moved the equal sign and the C squared over. Okay? That's all I did. You with me? So now we're going to go from Pythag, something so simple and pure, to the distance formula, which is bizarre, okay? But it's going to be okay. Here's step 2. How did I get there, right? I had him and I completely lost him. Here to here, nothing changes. We like that. How did I get from here to here? There. Let's go back to the top a little bit. Zoom out, please. The distance of A is x2 minus x1, right? Distance is subtraction. The difference between the x's is how long A is. So there's A. If A is that, can't I just switch them out? If I told you x is 4, couldn't you plug in 4 wherever x is? Right? It's because they're the same thing. Switch them out. Well, if these are the same thing, let's switch them out. I switched out A for x2 minus x1. And you're like, why would you do that? It looked so nice before. I know. B is y2 minus y1, so I switched that. Do you see how I left the parentheses so I could plug it in nicely? The whole thing still has to get squared at the end, right? I got to figure out what the length is first, and then I square it, right? Step 3. I got rid of the square here, didn't I? How do we cancel squares? What's the opposite of squares? If I say addition, the opposite is subtraction. If I say multiplication, the opposite is division. There's always a way to undo stuff. That's algebra, okay? So if we square something, we need a way to undo it. And the way to undo it is to root. We're going to root both sides. When I root here, it becomes, well, just C, right? It gets rid of the square. Over here, I go to root it. And a lot of people get confused about this. Let me show you what people do and why it's wrong. I know a Pythagorean triple. 3 numbers that when you put them in Pythag, work. 3 squared plus 5 squared equals, 4 squared. You didn't see that. Get that out in post. 3 squared plus 4 squared equals 5 squared. You can check it. What's 3 squared? 9! What's 4 squared? A fun game. 16. And what's 5 squared? 25. The only thing funnier than 24. All right, so does that check out? Is 9 plus 16 25? Oh, yeah, it is. So that checks out. Well, if we wanted to then, what if I wanted to get rid of that root? I'm sorry, that square. What would I do? You'd root it. Thank you for spoiling all the jokes, Mr. Mack. It's the 4th time I've done this today. You have to forgive me, YouTube. So I root both sides, right? Well, here, roots and squares cancel and I get 5, right? That's cool. A lot of people then think, oh, well, these cancel too, right? And we get 3 plus 4 equals 5. So for some reason, algebra doesn't like that. So we have to come up with y. So we're not allowed to do that. We're allowed to do it here. We're not allowed to do it there. If I do it here, I get 5. Here, I can't cancel those roots and squares for some reason. Is it valid the way it is? Can I leave it like that? What's 3 squared? 9. What's 4 squared? What's 9 plus 16? It's funnier than 24. 25. And that checks out, doesn't it? Root 25 is 5. So when we have 2 different ideas separated by a plus or a minus, you can't just root the whole thing and get rid of both. It doesn't work, okay? They're 2 separate terms. We have to leave them alone. That's as close as we can get, okay? If that was x squared and y squared, then that's as close as we can get there. We can't do any more. But because we use numbers, we could check it, right? So over here, it doesn't cancel the squares when we root it. We have to leave the root up there. And that's the distance formula. The length of C, because that's what bar C means, equals the root of everything, x2 minus x1 squared plus y2 minus y1 squared. That's a lot. And the way I said it is actually kind of confusing. Memorization is hard, but Pythag, if you start with it, it's not bad, right? A squared plus b squared equals c squared. We're going to work on getting from Pythag to there, because you're going to need to be able to explain it on a quiz and a test, how we get from one to the other and why they're connected. You need to do that in homework tonight, too. So here's what we're going to do. Take out a piece of graph paper. If you haven't got one, send somebody from your row to go get some for everybody. We're going to start with Pythag, and we're going to work our way down. Go, 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 go. Make your own right triangle. Remember, A and B can be either of the legs. Last time I had B being the vertical part, so just to mess with you guys, I'm going to have B be the horizontal part this time. You can label it however you want. Your formula might look a little bit different. It might have the y's before the x's, but it's all good, okay? So, Pythag, that's what it is, right? Put some dots. I like starting with the bottom left point. I don't know why, I just do. In the notes, I did the top left. Let's start here. Do we know that coordinate? Not really, right? There's no coordinate plane. But it's going to be something comma something. Something comma what? X comma y. Let's call those x1 and y1. Because they're the first ones we used. Now let's go up to this dot. What do they share? We can't just call it whatever we want. They share their x's, right? Thank you, Bailey. Thank you. I'm sorry. I should have waited to call on you. Because horizontally, they match up at the same time, right? If I move horizontally, I hit them at the same time. So their x's are the same. So that's an x1. Are their y's the same? Well, they better not, because it'd be the same point. They're different dots, right? Something has to be different. I hit this one vertically first and this one second, so I'm going to call that y sub 2. Are you hanging on? I'll give you a couple seconds for station identification. This is Mr. Mac's room. This is day number 2 of actual homework. Notes number 2, part 2. All right. So, bring you back. These two dots, what do they have in common? Are they the same horizontally? No, they're different, right? There's horizontal distance between them. Are they the same vertically? Yes. Vertically, they hit at the same time. So if that's a y1, that's a y1. And we already said horizontally they're different. So if that's x1, that's x2. All right? Give you a couple seconds to think. We don't need C. So A's distance is going to be vertical distance, right? It's vertical. So what variable deals with the up and down? Is it X or Y? Y. So it's going to be the difference between the values. What are our Y values? Y2 and Y1. That's the distance of A. How far they are apart vertically, right? B is horizontal in this example. So it's going to be how far they are apart horizontally. And that's x2 minus x1. Macy, I think we might need to move your seat. Better? All right. So in our Pythagorean theorem, we know that A is the same thing as y2 minus y1. So let's go back to Pythag. It's getting small again, Macy. I'm sorry. Here's a squared plus b squared equals c squared, right? Well, instead of squared, we're going to write something squared plus something else squared for b equals c squared. What are we going to substitute for a? We just found out that a is equal to what? Yes. Yep. And instead of b, we're going to substitute x2 minus x1. Because they are the same, right? That's what equal sign means. And now we're almost there. The hard part was kind of the diagram, right? Getting your x's and y's correct. Now this gives us a formula for c squared, right? If I want to know what c squared is, you can do that and plug it in, and boop, out pops c squared. But I don't care what c squared is. I want to know what the distance of c is, regular c. I don't know what the box is. I want to know the line. So what do I need to do to get rid of that square? Right? So I root both sides. Over here it cancels, right? Because it's one idea, one term. The root of c squared is c, by definition. Can we do anything more over here? Do those squares cancel? No. Common misconception. If you're not sure, plug in numbers and check, right? Is 3 squared plus 4 squared equal 5 squared still true when I cancel the squares? No. 3 plus 4 equals 5? No, that's not a thing. So here's our distance formula. And really, when you think about it, all it is a squared, right? That's a. It's just a weird way of writing a, y2 minus y1, right? A squared plus b squared all rooted equals c. It's just Pythag. Something squared plus something squared equals c squared, except we move the square over, right? That's A, that's B. In this example, A was vertical, right? So A is going to be the y ones. That's the distance formula. I want you to be able to show how you go from here to here. And I want you to be able to explain in words what this, why is A y2 minus y1? Well, it's the vertical component, right? So it's going to be the difference between the y's, because distance is subtraction. A lot of times people put plus signs here. That tells me they don't know what they're doing. They're just trying to remember something. Why would this be plus? It's distance. Distance is subtraction. Why would this be minus if they put a minus sign there? It's Pythagorean Theorem, for crying out loud. It's not a squared minus b squared equals c squared. It's a squared plus b squared. Of course it's a plus. And again, all of this stuff, these are mistakes you're going to make, and that's okay. I don't mean to make fun of you. What I mean is that once you understand it, you get to the point where how could it be anything else? And that's where I want to get you to. And the way to get you to do that is to practice going from one to the other and seeing those connections. Sometimes seeing is the hardest part of the math problem, seeing what's going on. That was definitely true for the homework last night, right? Seeing the connections. That's math. All the rest is calculation. Speaking of all the rest, the last page in the notes is just showing you how to use the distance formula. Here it is. Here are the points. Plug them in and see what you get, right? I'm going to trust you with that. I'm not going to go over it. I trust that you can plug in points and do the right thing. The hard part about this is that that's x1, y1, right? That's x2, y2. Don't goof them, okay? x2 and y2 come first here because usually they come later, which means they're bigger numbers. As long as you're consistent, you'll be fine. You'll have issues with it. We'll talk about it tomorrow, okay? Here's the homework. The first page is coordinate plane practice, plotting dots, right? I want to see if you can get them right. Then I've got some questions about the coordinate planes. The coordinate plane and their quadrants. On the second plane, or second page, I cannot talk today. I'm asking you to explain the connection between the distance formula and the Pythagorean theorem. That's what we just did. I want with words and with pictures. So don't just copy down this. Whoops, that's not it. It's somewhere. This. Don't just write that down and say, oh, I did it. I explained it. I need words to go with it. Why is A equal to y2 minus y1? Good God, why, right? Pretend I'm somebody that just joined geometry class. It's not obvious, right? So you point out that subtraction is difference. And A is the vertical component in the problem, right? Then after that, I have you do some distance formula practice, right? Using the formula, which I think is the least interesting part of all of this. Plugging in numbers and getting an answer is not real math. It's a part of math, but not the most exciting. If you have any questions on any of this stuff, let's talk about it, okay? The one thing I do want to show you is that there's a reason I show you the connection between the distance formula and the Pythagorean theorem. So 5, 6, and 7, it says use distance formula to find how far they are apart, right? So you got to figure out what the coordinates are. You got to count those boxes and then plug the numbers in, right? But you could be smart. I want you to still use the distance formula. We need practice plugging in numbers, okay? But you can be clever. Why not just count the boxes for that first one? Distance formula is how long it is. Count the boxes. That's how you can check your work, right? The second one, you can't just count the boxes because it's at an angle. It's not going to work out nicely. But guess what? Distance formula is the Pythagorean theorem. We know this, right? Horizontal component. Vertical component. How long is the horizontal? Well, Macy can't see, but it's 3 long down here, and it's 4 long here. So how long is that hypotenuse going to be? I didn't use distance formula. I used Pythag. 3 and 4. 3 squared is 9. 4 squared is 9 and 16 make 25. So this thing's 25, right? What did I forget? A squared plus B squared equals C squared. 25 is C squared. So I got to root it. What's the root of 25? Do you see how useful that is, knowing that I don't need to use distance formula? I can just use Pythag. Pythag's way easier. I want you to use both, though. Use Pythag to check, okay? Sometimes Pythag doesn't come out to nice numbers, like number 7. Because not every number works in the Pythagorean theorem nicely, right? Very few do. Well, I should say infinitely many of them do, but they're kind of rare. So this one has a length of 1, 2, 3, 4, 5, 6 at the bottom, and a height of 2. 2 squared is 4, 6 squared is 36, so it's 40. Root 40, right? Yeah. But it's true. So those are the answers. I want to see the work. I told you my math class would be like this. The answers are boring. Root 40, who cares? But why? Plug in the coordinates to the formula, figure it out, and then check it with Pythag if you want. That's basically what we just did. Okay. How do you feel about the first page? Easy peasy? All right, that's what I wanted. How do you feel about the second page? Woo, intimidating. That's a lot of blank space there, right? Do your best. Start with Pythag, right? A squared plus b squared equals c squared, and then find your way to the distance formula. And after you have that written down, explain your thoughts on the side in words, okay? Do the best you can. Page 3, the thing we just did, looks intimidating, and plugging in numbers sucks, right? But it's not hard, it's just time consuming. Okay? Be careful when you're plugging stuff in. Remember, my rule is, whenever you plug something in, no matter what you're plugging in, no matter where you're plugging it in, always wrap it in parentheses. Okay? And that'll prevent you from missing negatives. Give it a shot.